So, atomic absorption. Two groups already done atomic absorption in labs, so they are the experts. So I might call on you anytime during lecture. Uh-oh. All right. So just as a refresher before going into atomic absorption, what's the difference between absorption and emission spectroscopy? Let's get that out of our system before moving on, because there is atomic absorption and there's atomic emission. So let's be on the same page. Ted. Exactly. So atomic absorption is it's measuring the absorption of light. So looking at the specific wavelength, how much of the light has been absorbed versus transmitted. And that's going from ground state to excited state. So when the matter absorbs light, it's going from ground to excited. But then when the matter is emitting light, and that's the emission we are measuring, then it's going from excited state to ground state. So we're measuring emission. So which wavelength would be longer, the emission wavelength or the absorption wavelength of a particular matter? Exactly. And why is it lower energy? Why is the emitted light is of a lower energy than the absorbed light? Go ahead. Oh, Lauren, go ahead. Energy is lost as heat. Some of the energy is lost in heat, and the remainder of the energy is gone as emitted light. All right, so now we are back to absorption and emission principles, so we can continue with atomic absorption or atomic spectroscopy, which covers absorption and emission. We can do either measuring absorption or we can measure emission. With atomic absorption, it's commonly abbreviated as AAS, whereas atomic emission spectroscopy, AES. AES, sorry. So there are two kinds of atomic absorption spectroscopy. There's the flame atomic absorption spectroscopy with two groups did in the lab, whereas, and the others will be doing it next week. Whereas the electrothermal is, instead of a flame, you have a platform that is heated, where you put your sample on the platform, rather than the flame is what's causing the atomization. And we'll talk about the difference between the two. In emission spectroscopy, we have flame emission, and we have inductively coupled plasma atomic emission spectroscopy. So that's a mouthful. Inductively coupled plasma. Plasma is the source of atomization in this case. And we're going to differentiate inductively coupled plasma emission spectroscopy versus flame emission. We'll talk about the difference between the two. So atomic spectroscopy has a unique mission, unique application, which is really determining the content of minerals and toxicants that are heavy metals. So the minerals that are nutrients that are important for us, for our bodies, and important to, some of them are important for the label, like the calcium and iron and potassium now, and sodium for labeling purposes. And then also they have the toxicant that you don't want to have heavy metal like lead and mercury and nickel and cadmium, arsenic. These are all toxicant that you want to measure and make sure they're present below the level that is action level. That means unacceptable level. Okay, so all those in pink from your periodic table can be determined using atomic absorption or emission spectroscopy. So they are categorized as essential nutrients, and there are several of them. Here I'm just listing few. Table 9.1 in your book lists all of them. And then there are toxic elements. Also there are others in the table. And then the USDA nutrient database has information about several minerals in different reference foods. But not all of the, it's not a complete database yet for all of the minerals or the nutrients for all of the different reference foods. So it's not complete, but they have some. And also they're listed in table 9.1 for FYI. Okay, so again, this is briefly the principle, absorption. This is based on electronic energy, because here we are measuring absorption or emission of a singular atom in the gaseous state. So as a singular atom, that means you don't have vibration, you don't have rotation, you have just the electronic energy. That electronic energy that has to do with the electron, I need to change battery for this, for the electron jumping to a higher shell, and by doing so it's going to the excited state, and then that's the absorption of light, of the photon of light, and then the emission of photon is when it's going back to its ground state and back to the lower energy level or lower shell. So every element in its gaseous state, it will absorb at a different wavelength. So it has a unique spectrum with unique lambda max, which is the wavelength at which we get highest absorption or highest fluorescence. As you can see, the lambda for absorption is of a lower wavelength than the lambda for emissions. So these are two different elements, A and B, and they do differ in their absorptivity or in their spectra. So again, here I'm reminding you that we don't have vibration or rotational energy, we have electronic energy, and these levels are, the jumping from one level to the other are unique for each element. That's why you have different spectra for each element. So only the allowable energy shifts. When the photon hits, the atom will absorb only in its allowable energy shifts. So you have to remember that. So if the energy that is bombarding that atom is within its potential energy shifts, then it will absorb light. If it's not within its potential energy shifts, it will not absorb light. And that's why we have different spectra for different matter. Okay. So in atomic spectroscopy, the very first step when your sample is in solution, when your minerals are in solution, the very first step is to aspirate that solution into fine mist. And some of you done that in the lab already, others will be doing that next week. So your sample would be aspirated into fine mist, and the sample is containing your minerals in a molecular form. And then it hits the flame. So the fine mist is projected onto a flame or plasma. There, your solvent is vaporizing, and then your molecular bonds are breaking, and then you end up with atoms in a gaseous state. So here it is, you have your solution, you have your element of interest in a molecular form, you get the desolvation, so that means the evaporation, and then you end up with your solid. The solid also vaporizes into gas, and then you get the atomization with the excess energy that you have from the flame due to the heat of the flame or the heat of the plasma. And then the atom absorbs light. Now, one thing we do not want to happen is you do not want your atom to ionize. So if the flame is too hot, your atoms may ionize. And if they do, then they absorb light differently. So you want to make sure that you measure in the atom state, not in the ion state. So you really want to measure here. You want to excite the atom rather than exciting the ion. So you excite the atom and it goes into an excited state, and that's when you measure absorption. If you measure absorption of the ion, the absorption is going to be different. Sometimes it's less sensitive than the absorption of an atom. Okay, so the flame is your source of atomization, the flame or the plasma. In other words, the heat that the flame is giving or the plasma is giving, the heat energy, is causing that atomization. Now, once atomized, you want that to be excited. So the source of excitation, the source of energy or light energy, is your cathode lamp or hollow cathode lamp. This is the most common lamp in atomic spectroscopy. The most common radiation source, I would say, and that's what you're going to use in the lab. So in a hollow cathode lamp, which looks like that down here, is basically a hollow tube from the hollow name, and it's filled with an inert gas, so it's either argon or neon. And then you have your anode and cathode, because there is going to be a voltage applied, so you will have electric signal. So you have an anode and you have a cathode. The anode is made of tungsten, that's anode, and the cathode is made of the metallic form of the element being measured. So if you're measuring iron, your cathode is made of the metallic form of iron. If you're measuring calcium, it's made up of the metallic form of calcium, and so on. Why is that? Because once it gets the voltage sources applied, the cathode is going to emit radiation in the spectra of that particular element, which is very important for determining absorption. You want the exact spectra of that element, and then you would deduce the absorption at a particular wavelength for that element. So that exact right radiation or energy that will allow the atom to get excited is what we need. And often we want to change the lamp for different elemental analysis, because you need the lamp to have that cathode of the metallic form. So sometimes calcium and magnesium, for example, lamp have both cathodes in it. So it has the calcium cathode and the magnesium cathode in that same lamp. Other lamps have only one cathode. So for example, the lamps that you're going to use in the lab have only either iron or calcium. So you have to change them in between analyses. This is a less common source of energy. It's electrodeless, so there is no voltage in this case. What happens is, again, there's a hollow tube and it has an inert gas, and again it has the element of interest, but the discharge or the energy is produced through radio frequency generator coil instead of an electric current. So that radio frequency is going to excite the cathode or the metallic form in your lamp that will allow it to emit spectra in that particular energy for that element. It's used for volatile elements generally, But like I said, most atomic spectroscopy units have the hollow cathode lamps. So we've gone through generations of atomic absorption units in the teaching lab. When I first came, there was a pathetic old atomic absorption unit that died maybe within a couple of years of me starting here. And then we obtained a newer version, but it's still old. And then now there is even a third version of atomic absorption that is working perfectly fine, but I don't have a picture of it. But anyway, all had the similar components. So you're going to have a little tube where you insert in your solution that has your minerals, and there is where your solution is going to be aspirated into the system, and mists or the solution will be converted to small droplets that is directed towards the flame. So this compartment here, you will ignite a flame, and it's very cool to ignite the flame. And the way you have a flame is basically you have a source of oxygen and source of fuel. So you will have containers for air, example air, and acetylene as fuel. And the amount of air mixed with fuel is kind of optimized to give you the optimum temperature of the flame. You don't want it to be too hot, it will cause ionization, and you don't want it to be relatively cold. I mean, a flame can be cold, but relatively low temperature. Otherwise, you don't get atomization. You don't have enough energy to break the bonds. So you really want to have enough or optimized flame, and that you modify by the extent of air mixed with acetylene. So then, so you have the flame generated, your sample is being aspirated. So if you can see here, there's a flask with a sample, and then the tubing is inserted in there. And the sample is aspirated into the flame, it gets atomized, and then on the far right, there is a compartment in both of these units, and in there, this compartment opens, and that's where you put your lamp. So the lamp is in there, and once a voltage is applied, the lamp will produce the light that is within the spectra based on the cathode, and the light is going to be projected towards the flame. So now your atoms that are in the gaseous form in the flame are going to be hit by the light. So then they will absorb, get excited, absorb light, and then the transmitted light is going to continue, and inside of the equipment, which you cannot see, is the detector. And we'll talk about the detector in a minute. So the detector would detect the emitted, not the emitted light, I'm sorry, the transmitted light at a particular wavelength. There is a monochromator in there that would select that wavelength that you would have maximum absorption, and that's where you do your measurement. That's an animation of it all. So that's your sample, and the aspirator, the flame, and the lamp. There's the incident beam, and there's the transmitted beam, and then there's your detector right there. And this absorption follows Beer's law, where is absorption equals A, the absorptivity, B, the length of your cell, and in this case, the flame is your cell, is your sample compartment. And then C is the concentration. So this demonstrates further what happens. So you have your flame with the sample in it. You have the cathode that emits radiation that is element specific. Then it goes through your sample, within it, calcium or iron or whatever element you are measuring, absorb a particular light at a particular wavelength that you can select using a monochromator. You pre-selected, you already know what is the, where you have maximum absorption. You already know, you select for that. And then the transmitted light get detected by a photomultiplier tube detector we talked about last time. And then the transmission gets converted to absorption, and then you get your readout. So the photomultiplier tube, it's important for you to remember. So we have the cathode here and then an anode, but then when the radiation hits the cathode, electron is emitted and it hits a dynode, and then your electrons gets multiplied from one dynode to another, and then you get really an amplified signal. So photomultiplier tube detector is the detector that we have in our atomic spectroscopy unit. Electrothermal or graphite furnace, AA, it's not very common. You don't find it a lot in labs. It's just a more expensive instrument, and it has low sample throughput. That means you cannot analyze a lot of samples in a short period of time. So why is that? Because the way it works is a little bit different than the flame. So instead of having a flame, you have a compartment. So graphite tube, and in there's a platform that is heated to really high temperature. On that platform, you spot your sample. So you spot your sample, and then you close it, you increase the temperature, and then with the high temperature, your sample volatilizes, atoms are broken off from molecules, breaking off the bonds, and they get into the gaseous state. And the rest of the principle is basically the same. You have a light source, you have your detector, and all of that is almost the same. So one benefit of it, or a couple of benefits, is you can use smaller samples. You'll see when you do the lab, or those of you already did the lab saw, that you really have to prepare enough sample because the aspirator is going to take a few, it needs a little bit of sample to aspirate into the flame, and it goes really fast. So if you don't have enough sample, you won't have enough mist brought up to the flame. Whereas here, you don't have that issue. You spot whatever sample you have. If you have only 1 ml, you might only need 100 microliters, and that should be enough because you have low threshold. So that this is kind of the advantage of that. But it's really more difficult to operate given the complexity of the graphic tube and how you put the sample in. You need to wait until it cools between different samples in order to get the measurement. So moving on to flame emission, you can ask questions. I think I'm not stopping for questions, but you can stop me. Give me a break from talking. No? Okay. So flame emission, in this case, the flame is the source of atomization and the source of excitation. So here there is no lamp, basically. So your sample goes into the flame, is atomized, and it's excited, and then the emitted photons of light are what gets measured. Now, but this does not apply for all of the elements. It can only be used for elements that require relatively low excitement energy, such as sodium and potassium. So sodium and potassium often are analyzed with flame emission spectroscopy because the flame is enough to not only atomize but to excite the atoms. Again, in flame emission, you have the same principle. You need to atomize. This is a must. So atomization is required, and once in the atom state, the actual heat of the flame can cause excitation. There are two forms. There's flame emission spectroscopy, and then there is flame photometry. So when you hear flame photometry, you know you don't have a monochromator in your detector. You have a filter. So basically, the light gets filtered rather than gets grated. And here you have low flame temperature, and you have low interference because not all minerals get excited or elements get excited at low temperatures. Only your elements of interest would be excited at this low temperature. So it can be really used for sodium and potassium, for example. There are some recap questions that we're going to skip for now. And then here I'm going to focus a little bit more on ICP, which is inductively coupled plasma atomic emission spectroscopy, which is a more advanced tool, and now it's replacing the atomic absorption spectroscopy, or the flame atomic absorption spectroscopy. It's replacing it because it has a lot of advantages that we're going to talk about here in a little bit. So in inductively coupled plasma, AES, what happens here, you have a plasma, and it is the source of atomization and excitation. So the plasma is basically composed of argon gas. Argon gas has high concentration of cations and electrons, so it's really ionized gas. And when it gets heated, it becomes plasma. So it gets heated by radio frequency power applied to copper coil. So this is going to heat the argon gas and bring it up to really high temperature, generating your plasma. So here's a breakout of the ICP. So again, you have your sample. It's pumped into a nebulizer, which you get, nebulizer is what converts the stream of your liquid into mist. And then you have the argon gas source. And then here you have a copper coil where the radio frequency power is applied, and it transfers the energy to the free electrons within your argon gas, and then generating that plasma, which is very, very hot. And in there, your sample that are in molecules, your element in molecular form are going to be, the bonds are going to be broken into atoms, and then the atoms are going to be excited. And the emitted radiation is going to go into a grating system, and light is going to be diffracted. And some units have multiple photomultiplier tubes. So you have not only one, you can have multiple in one unit, and that allows simultaneous detection of several elements at a time. So you can have 8 photomultiplier tubes in there, and you get detection of 8 different elements at a time. So that's one more advantage that the current flame atomic absorption spectroscopy has. So you can either do do this simultaneously. Some lower end units have only one photomultiplier tube in here, and you can get sequential reading. So you can, while the sample is there, you can select different wavelength, and then you get absorption one after the other. Another type of detector is the charge injection detector. We'll talk about it in a minute. It also diffracts. There's a diffraction of light using prism and grating system, and then they all get projected onto this kind of detector, and you get a spectrum. So instead of just absorption at one wavelength, you can actually get a spectrum of absorption. So you get simultaneous reading for many elements at a time, more than having multiple photomultiplier tubes. Oh, this is just another image of the plasma and the different temperatures within that plasma. That's not very important, but what you want to know is there's your argon gas, there is the copper coil that get radio frequency and that heats up or produces the plasma by exciting the electrons or providing energy to the electrons in the argon gas. Sequential, we talked about it, photomultiplier tube, where you have one detector and then you can change the wavelength and get multiple readings sequentially and rapidly. Simultaneous is when you have multiple, usually 8, and then you can get multiple elements determined simultaneously. The ISHO spectrometer is really high-end detector for ICP, and it basically has either a charge injection detector or charge coupled device, which I'm not going to go into the difference between these, but the idea is your light gets diffracted using a prism and also using a grating system, and then all of the different wavelengths reach the detector simultaneously, so you can get detection of multiple elements, a large number of elements simultaneously. So that's a very efficient unit to have, but again, it's very expensive. As you can see, it's $70,000 to $90,000. So it's quite expensive, but in industry, they can afford expensive instrument because they are rich, so they can have it. But institutions like teaching students, we are poor, we can't have it, so you have your old flame atomic absorption spectroscopy. Okay. So how do we prepare our samples for analysis? So for atomic absorption lab, you already have your sample ashed for you. So the first step to determine mineral is you really want to release your elements from the organic matter. So you can do that by dry ashing or wet ashing. So dry ashing is basically you put your sample in a muffle furnace and you put it at high temperature. So at really high temperature, around 480 to 500 degrees C, all your organic matter incinerate, so oxidize. So you get CO2, of course water evaporates, CO2, NO2, SO2, everything turn into gaseous state, or your organic matter, and what remains we call ash, and that is your minerals. No vitamins. People confuse the ash content and they would say minerals and vitamins. Vitamins is also an organic matter and it will incinerate. You can do wet ashing, and wet ashing is sometimes desirable for elements that are volatile. So for example, iron and zinc are volatile elements, so they can easily volatilize during ashing, so you end up with underestimation. So if you run your samples in the lab and you got an underestimated iron content, pretty much could be that your iron part of it got volatilized. Okay, that is why in industry, for iron detection, for labeling, they go with wet ashing. Because in wet ashing, you use lower temperature, but you use acids to digest and oxidize your organic matter. So a combination of acid and heat gives you the result of a dry ashing, where all of your organic matter gets oxidized and evaporates. So we'll talk more about dry ashing and wet ashing in the minerals section or chapter, but this is the main difference, is basically you are getting rid of organic matter and leaving your minerals for detection. Sometimes you can do direct injection. That is only in samples that you don't have that much of a interference with the organic matter. It's very uncommon. All right, so I have here reagents, blank, standards, and labware. Why are these important? It's very important to have a blank. Those of you that did the lab, why is a blank important? You don't remember? You didn't talk about blank? Groups C and D? What? You're right in terms of contamination. So if there are any minerals in the that comes from reagents really that you use HCl and well, mainly HCl, and you also use lanthanum chloride. You'll learn about that if you haven't done the lab. So sometimes reagents do carry minerals in them, contaminants. So you have to have a blank that does not include your sample or your ashed sample, so that if there is any interference from a contaminant, you correct for that. You subtract the absorption of the blank from the absorption of the sample. Standards, we run standards. Usually we get really very high purity standards, over 98% purity. And these standards are needed to construct a standard curve. You prepare your standard at different concentrations to ensure a linear standard curve, and then you dilute the sample to fall within your linear standard curve. Labware, so Cindy and Lucy made sure that whatever you're using in the lab is mineral free or elemental analysis free. You don't want glassware that has contamination, because one glassware might be contaminated, the other might not. So if you're doing a replication or if you're preparing your standard, one standard was prepared in a contaminated glassware where another was not. So that is going to screw up your results. So they spent hours on an end washing all of the labware with acid. They're all acid washed to solubilize any residual elements or minerals in the glassware before you actually use them in the lab. And the crucibles that are used also for ashing, all of them has been acid washed before putting samples in them and ashing them in the muffle furnace. So Lucy can speak to the hours that she spent doing that in order for the lab to work for you guys. So thank her when you get a chance. Okay. Calibration is very important. So like I said, we select really high purity standards, and we want to make sure that we don't get a graph like this. We don't want any plateauing. Then your sample, if it's up here, it won't be detected accurately, because this is not a linear relationship. So you want to select concentrations where you do have a linear relationship, and you plot a linear line and get the equation of the line. So you will notice that for iron, linearity is at much lower concentration than for calcium. So the standards are prepared at different concentrations. And then depending on your food sample, different food samples are diluted differently. So if it's a cheese sample, you have to dilute it quite a bit for calcium analysis versus a flour sample that does not necessarily have high calcium content. So dilution is important so that you fit the linear curve. Now, life is not perfect, and there's always interference. So we have interferences we call spectral interferences. So for example, iron and zinc have the same or very similar lambda max. So if we put our atomic absorption monochromator at one wavelength that is optimum for iron, it would be the same as zinc, and I'll be measuring both iron and zinc and call it iron. So what I do in this case is specifically for the analysis of iron, I select a wavelength that's not necessarily the optimal, but something that still gives me an absorption, another wavelength that gives me an absorption. And same for zinc, selecting a different wavelength, not necessarily the lambda max in this case. Background incomplete atomization. So incomplete atomization comes from when your flame is basically not really hot enough. So your molecule doesn't break into atoms, and what happens, it's a large molecule in the flame, and when the light hits it, instead of absorbing light, it's going to scatter light. And if it scatters light, the transmitted light is going to be less. So the computer program is going to interpret this as higher absorption because less transmittance reached the detector. So that incomplete atomization causes overestimation. One thing I forgot to mention that might cause underestimation, for example, if you're ashing a sample and you look at your ash and it's still really dark black ash, that means you still have carbon matter. And if you still have carbon matter, you still have some minerals entrapped with your carbon matter. So you might underestimate. So all of this is important when you are discussing your results in your lab report. So make sure you take note of that. I won't be here next week to discuss with you questions in lab, those of you that are doing atomic absorption. So here you go. Transport interferences. That means if your sample is different, you have difference matrix, difference in viscosity or conductivity or whatever, any differences in the sample that is different than the standard, what we want to make sure is the standard is prepared the same way that the sample has been prepared. Similar reagents and similar water source and all of that to avoid matrix interferences or transport interferences specifically. Solute volatilization, this is really important in the case of calcium, and you'll do this in the lab. Calcium has a tendency to form big compounds with phosphates. So like in cheese, you have a lot of calcium and a lot of phosphate. So you have what is known as calcium pyrophosphate formed, which is a huge molecule with a lot of calcium and a lot of phosphates interacting with each other. So when you form that large molecule, this molecule is not, first of all, it might precipitate. So it might not go in the mist anyway. It might not be aspirated. And if you got some of the pyrophosphates there, it will not volatilize. It will precipitate before reaching the flame. So it will not volatilize into the flame. So that causes an underestimation for your calcium. So what we do, we add something we call lanthanum chloride. So the lanthanum in there is going to react with the phosphorus. It will displace calcium and react with the phosphorus, freeing the calcium, helping it to get into solution so it can be detected. Okay? So the lanthanum chloride, the lanthanum will react with the phosphorus, preventing the formation of calcium pyrophosphates. If you don't add enough lanthanum chloride, that will end up with underestimation of your calcium. Ionization is another interference if the flame is too hot. So Cindy works hard on optimizing your flame. So we get atomization, we don't get ionization. Too cold of the flame, you don't get atomization. Too hot of a flame, you get ionization. So it's really very tricky, and it's very important to optimize it, because if some of your atoms ionize, you get lower absorption, you get underestimation. Last slide. So here's comparison. Both measure trace metal concentration. They are of excellent precision and accuracy. So, however, AA has a little bit of an advantage over ICP because it's an older unit, an older technique in a sense that all of the ins and outs have been identified. So interferences have been identified, and we know how to overcome. It's widely available, cheaper instrument, so a lot of people still use AA. ICP, the main advantage is you can detect multiple elements in a single sample. And the sample is stable at high temperature, so there is no chance of ionization. This is very important. I didn't mention it before. In plasma, because of the high ions in plasma, they would prevent the ionization of your atoms, the presence of high ions in the plasma. So really, you don't have to worry about the plasma being too hot, so you don't have ionization. So stable. And then detection limit is really low for ICP compared to AA. You can find those differences in table 9. I think your slide says 24 or something. This is old version. But table 9, 5 is where you would find that information about detection limits. All right, so before you leave, I just want to remind you that next week you have Ted Labuza teaching water, 3 lectures. I posted the lectures already online. And then in lab, you will be on with Lucy and Cindy for AA, and then Rachel and Kati for MS. So Kati is replacing me for the MS. So any information other than, oh, and the test, remember, is on Monday, the 29th. And it ends here with the material here. So Ted's lectures are not included on the test. To study and prepare for the test, please review previous tests and quizzes. Look at quiz 2 and test 1 from last year. I've changed this year a little bit. We don't have 4 quizzes. We have 3 quizzes. So there is quiz 2 material that from last year that would be helpful for you to look at, as well as exam 1 from last year. And today I will upload answers to questions for GC and HPLC. Unfortunately not the AA and MS because some of you still have to write that report. And in terms of lab reports, I'm still grading the GC and LC. I'll take them with me and grade on the plane. I leave tomorrow. But to compensate for not having your lab reports, I will put today, I graded a couple, so I will put today on the web an example lab report so that this helps you with preparing your next full lab report. Okay, so any questions for me? I'm gonna miss you guys. No, I will not. No, I won't have time to think about it.